So, kinetics of absorption of energy. Now, this absorption of energy, we are talking about absorption induced by the RF or stimulated by the RF. Okay, now we are talking about absorption of energy on application of the RF. Yeah. So, let's consider the two energy levels once more. Let's say the population here is an alpha, population here is an beta, and the transition probability caused by the RF is P. Now we notice this transition probability is the same upward or downward. This is RF induced. So RF induced, what is the transition probability? Einstein's transition probability equation, proportional to, here we have the final state, the perturbation, initial state, square. Right? This is the transition probability equation which you done in any, this is valid for any spectroscopy, not only for NMR, but it is true for any spectroscopy condition. Here you have a final state, and you notice that this equation is symmetric. So whether you put F here and I here and I here and F there is the same. And this is called as, we call it as P. P is proportional to the transition probability, and this is final state, initial state, and this is symmetric because of the modulus square. Okay, and therefore the transition probabilities up and down are the same. So let us call this as you can actually put in the perturbation here explicitly. What will be the perturbation? Perturbation will be interaction between the magnetic moment and the H1 field. Okay, so this, and in fact this is the Hamiltonian here. This is the perturbation Hamiltonian, and perturbation Hamiltonian is minus mu dot H1. Mu H1, right? Mu is the magnetic moment, interaction is with the H1 field. This interaction energy, then I convert them into the operators, then you have the interaction perturbation.
So, in previous class you defined another transition probability W alpha beta and beta alpha. So how?
That includes the lattice.
Includes the, so
that includes, here the lattice is not included.
Between two
same two levels.
So the W alpha beta and W beta alpha are they not same in that?
They are not same. They are not. That is actually, this is because of the coupling to the lattice. So there the transitions are caused by the fluctuations in the lattice, and if there is an energy released here, there has to be somebody to take that energy. There is a coupling. There is a coupling between the spin system and the lattice. Okay? Energy released here will be absorbed there, and energy required here will be taken from there. And therefore this is intimately connected with the populations of the energy levels in the lattice.
So W alpha beta term,
yes,
that includes the population.
Yes, in the lattice, yeah. So that explicitly, if you want to see that, you can actually look at Schlichter's book. This is explicitly detailed in Schlichter's book. So you consider the energy levels. In fact, I have that.
So in that case, you just cannot bring in the quantum mechanical description of transition between two quantum levels, because in that case.
No, there you are taking the total transition probability. You are taking the total transition probability, which is induced by the lattice. Here it is RF induced. So I have a particular stimulant. RF is applied externally, and I am calculating what is the transition probability due to this only. Okay, and the net transition, if you want to calculate, you have to include this plus that. Finally, when you want to do the calculation with regard to the energy absorption, you have to include this one plus the relaxation induced transitions. Okay, so we are going in steps. We are first considering what is the induced probability and what happens if you don't consider that. That also we have to see what are the consequences. Suppose you only had there is no relaxation happening. What is the consequence of that? So we will see that also. So for that you should be able to calculate from here. And this you will see, this is the, since the H1 is applied in the transverse plane, it is either the Hx or the Hy. H1 is on the x-axis, right? X or the y-axis, wherever it is applied. So therefore, the component of the mu will be the mu x. So the mu x, if I put in here, there, and it turns out that it will only have a non-zero value if this and this have delta m is equal to plus minus 1. So selection rules come from there. Okay. But that is, now you take it that the perturbation, this one is given by 1 by 4 gamma square H1 square. Gamma is the galvanic ratio and H1 is the amplitude of your RF. This comes simply from this calculation. So now you write the rate equations for this. dn alpha by dt is equal to P.
So this mu, you will take in x direction, mu x.
Because it's the dot product. So since your H1 is in the x-axis, then it will be mu x. But if H1 is on the y-axis, it will be mu y.
Net is in the net mu in the z direction.
Net what?
Mu is in the z direction.
No. So what is the perturbation? H1 is causing the perturbation. H1 field is causing the perturbation, which is causing the transition. Okay. So interaction between the two is between the magnetic moment in the H1 is what we are considering. What is the perturbation? Okay, H0 is the main Hamiltonian is there, that's fine. But the perturbation is due to the interaction between your H1 field and the mu. And therefore that is what enters here. The perturbation has to be extremely weak compared to your main interaction. Then only perturbation theory is well. So when you do that, then this is what you will get. What is the it causes the transition.
Sir, but you can make a dot product of mu and H1 and here is on the z-axis and H1.
No, mu is not on the z-axis. Mu is a vector. Mu is a vector, H1 is a vector. Okay, in this when you say that. What is the dot? If H1, anything between the orthogonal components is 0, dot product of orthogonal components is 0. Whichever is along that same direction only survives. When I say mu dot H naught, what do I get? Mu z H naught. Correct? So but the mu has components in other directions also. You have mu x and mu y also, but they don't appear.
So they cancel out.
They cancel out. No, interact dot product is 0. Dot product is 0. Not cancelling out. The dot product is 0. In the interaction, the dot product is 0. So here in the interaction, only the x component survives. Other dot products are 0. P n beta minus n alpha. Similarly, you can write for, we wrote these equations earlier also, except that I have now written P instead of W beta alpha, W alpha beta. Okay. So once again I will write an equation which is some arbitrary number. What is the equation number I have here? 1.58. 47 was last. Okay. So this is 1.5 y, in fact 9. I had written it afterwards, but it doesn't matter. Okay. Now you can rewrite this as half dn by dt, because n is equal to n alpha is equal to half n plus small n. This capital N is sum of the two, and this is, and n is a constant, and therefore that will be here. And this is equal to minus Pn. Dn alpha, this is the left hand side. This is the left hand side, and the right hand side is this. Okay. So I should write it in that manner, no? So the left hand side is half dn by dt, and the right hand side, this is minus Pn. Minus Pn because this is n beta minus n alpha. And this one is my 1.61. So this can be easily solved, right? Half dn by dt, therefore dn by dt is equal to minus 2 Pn. So actually this is 1.61. This is 1.60. This is 1.61. And what is the solution of this? N0, not N0. Here it is n at time t is equal to 0, e to the minus 2p. Right? So as time increases, this goes to 0. The population difference goes to 0. What does it mean? If a population difference goes to 0, right? So if I apply RF for a long period of time, signal will vanish. Because n of t goes to 0, then it means there is no signal. So therefore I can write energy absorbed, rate of energy absorption, dE by dt is equal to n alpha P E beta minus E alpha. This is energy absorbed and this is energy released, n alpha P E beta minus E alpha. So this factor, that delta E is the same. So this is equal to n P delta E. And yeah, n beta. So therefore this is equal to P delta E n of 0 e to the minus 2 pt. And this is my 1.65. So if I plot dE by dt versus time, initially it is maximum energy and then it goes to 0. or if I integrate this equation and get the energy absorbed, integrate to get energy absorbed as a function of time, we'll get E is a saturation. So this is saturation. Okay. So after some time, you have no signal. How long it takes to reach this condition? Very rapidly, because the population differences are very small. Population differences are extremely small. Therefore, very rapidly you will see that the two things equilibrate and there will be no signal. But you always get signal, right? In fact, and that happens because of the relaxation. There is somebody who is trying to restore this population difference continuously, which compensates for the energy, the saturation which is created by this P induced transition. Therefore, you will always have a signal. So here I should tell you a story and then stop, and that is the Gorter, who actually did the first experiment on nuclear magnetic resonance way back in 1940, before 1942-43. That is it. So he actually messed the resonance because of this factor. He chose a sample which has very long relaxation times. So it is a very long time for it to cross transitions. It depends on the system. It depends on the lattice, how good the lattice is in causing transitions. So therefore, he chose a system which had very long relaxation times. So as soon as he applied the RF, in no time it was saturated. So he didn't observe the signal at all. So he missed the Nobel Prize. So you see, choice of the sample is crucial. Okay. So